Can you hear me okay? Excellent. I'd like to introduce Dr. Eva Bagg. She is the President and Superintendent of Barstow Community College.
Thank you, Anthony. Welcome, everybody. I see our room is filling up here, and I just want to say thank you for everyone for attending this morning, all the faculty, the students, and community members. We are so pleased to start this collaboration with NASA, and this lecture this morning we hope is the first of many activities, educational activities for our community and our students. At this time, I would like to thank a couple of individuals who've really been working behind the scenes for quite some time and helping to bring this first lecture to us. Leslie Kunkelman with Goldstone Outreach at the NASA Goldstone Visitor Center, Deep Space Network. Leslie, thank you so much. And Heather Doyle, the manager for the Solar System Public Engagement and Network of NASA Jet Propulsion Laboratory in Pasadena. Just want to thank you both so much for bringing Mr. Scott this lecture here to our college. So with that, I'll pass it over to you, Heather, with much gratitude.
Well, and thank you for having us. And it's my pleasure to introduce Charles, or Chuck, Scott. He's the InSight project manager at JPL. So InSight is a lander at Mars right now. And Chuck was the flight system manager on InSight prior to launch, and then assumed the role of deputy project manager post-launch, which was in May of 2018, and project manager in November of 2019. InSight successfully landed on Mars the Monday after Thanksgiving and has been studying the deep interior since. Chuck has over 30 years of spaceflight operations experience at JPL and 20 years of project line management experience. Chuck also has 3 years of experience as manager of development and operations for Dryden Aeronautical Test Range under Spiral Technologies at NASA Armstrong. He has a BS degree in computer science and engineering from Northern State University and has received several awards. Please put any questions you have for Chuck in the chat box during our presentation, and Leslie Kunkelman will be collecting them throughout to ask them to him at the end. So if you have any technical difficulties, please hang in there with us. You know, as we all know, doing things online these days, sometimes, you know, noises in the background happen, so I might mute you, or, you know, if we have any issues with bandwidth, we might ask you to turn off your camera. Just hang in there. Sometimes even just logging out of the talk and then logging back in can help. And with that, I turn the time over to you, Mr. Scott. Really looking forward to this presentation, given the fact that Perseverance is going to be launching at the end of this month. Really super exciting. So thank you for coming to talk to us about it.
Thank you, Heather. I appreciate it. I'm assuming everybody can hear me. Excited to be able to give this presentation to you on the precipice of launching Perseverance for it to join us on Mars. As Heather said, she gave a little background on me. I'll give a little additional before I start. I'm actually, I live fairly local. I'm in the high desert in Palmdale, and actually commute down to JPL every day. Well, not lately, but I have been. I'm a second generation JPLer. My dad started JPL in 1957 and worked on the navigation systems and everything that were used during Ranger and Mariner. And he retired out of JPL and about the time I was starting. So, and I've been there for a long time, as Heather said. And I did have a short stint up at, it was NASA Dryden at the time, working in the test range with the experimental aircraft up at Armstrong. So today we're going to talk a little bit, or my agenda is kind of to talk a little bit about Mars and some exploration history of Mars, excuse me, and then some details about the rover and what's coming up. So with that, I'll get started. So this is Mars, how we kind of know it now, because of course we have beautiful imaging from the orbiters we have around Mars. Being MRO, especially, they get high-resolution images from Mars Reconnaissance Orbiter and Odyssey, and then, of course, ESA orbiters, Mars Express and TGO. So when you look at the night sky, what you really see of Mars is something like this, which you probably don't see much on your screen, but in the center there's a little dot. And that's about how you see it from Earth with the naked eye. Now, Mars was studied back in the 1800s, and so when you study it with a telescope, back then you might see something more like this. Depending on where you are in the orbit with Earth and Mars, they're at opposition. When you're at the closest approach, then you can see more. And so it was studied back in the mid to late 1800s by Schiaparelli, Schiaparelli, and he made this map up of what he thought was the continents and what he called channels on Mars. And so there's a quote from Schiaparelli that says that is this one: rather than true channels to form familiar to us, we must imagine depressions in the soil that are not very deep and extend straight direction for thousands of miles, a width of 100 to 200 kilometers and maybe more. Where he pointed out that the absence of rain on Mars, these channels probably the main mechanism for which water and with it organic life can spread on the dry surface of the planet. So that was a quote he had made back in 1893 after the studies he had made of Mars. And what was found later, and that he actually corrected later, was that those channels, or what he was seeing, was an optical illusion from the telescope and what he was using. And so they found that, of course, there weren't these channels on Mars, but just to kind of show you how things continue to evolve, I believe it was about 8 years later or so, longer than that. I guess it was in 1909. There's an article in the New York Times where Lowell, who had built the Lowell Observatory in Arizona, and he did observations of Mars also, and of course he saw these same channels because he was still seeing these optical illusions on what he was looking through, and got together with a writer from the New York Times and wrote, "There's life on the planet Mars." And this was kind of an example where they had written kind of science fiction unintentionally, because that's not really how Mars looked and what we've later discovered since then. Now, of course, the next really in-depth discovery or study of Mars happened much later, about 50 years later, when Mariner 4, which is a JPL mission, flew by Mars and took images of Mars, and we're able to get more detailed images of what the surface of Mars looked like. And so if you look kind of, you can actually Google search or whatever these, you can find lots of images from Mariner 4. And this gives you some amount of idea, or gave them some amount of idea of what the surface of Mars was like. And what you have to remember back then is they had just finished doing some of the surveyors on the moon, and they had finished up the Ranger series impacting on the moon. And so navigating to Mars and getting an image of the planet Mars was quite an accomplishment by 1965 on Mariner 4. The next more in-depth discovery, the next more in-depth study of Mars happened about 10 years later. In 1975, a Russian lander landed, called Venera 9, landed on Mars and gave an idea that portions of Mars can be very rocky. And so this was images that had been sent back, and shows kind of the terrain of Mars based on where they had landed. If we go forward a little bit further, not too much, later in 1975, we launched Viking. And those were JPL missions, 2 Viking spacecraft that contained an orbiter and a lander for each. And so they both landed on different parts of the planet. And they sent back quite amazing imagery because, of course, we had improved our imaging by then. So this is images from the Viking, one of the Viking orbiters. And then this is a picture from one of the Viking landers. And so there you can still see that it's fairly rocky where they had landed, although they had thought it seemed smooth and it was going to be a nice landing site. And then this is from Viking also, where you can see that this terrain, you know, could be fairly rough. Although their imaging from orbit seemed to be smooth enough for landing, there was a lot of rocks, and that just kind of goes to show you how accurate the imaging was. You know, it still was not as detailed or nearly as detailed as what we get from MRO now. The next exploration of Mars was about 21 years later, which was Sojourner, landed on Mars, and that landed using a new technique of, instead of having powered landing all the way down, of using rockets to slow down and to actually allow you to land. They used this airbag technique, where everything for the lander and the base part of the mission and the enclosed rover was all in this giant airbag, and it came down and it landed and kind of bounced around, stopped, then opened up like a flower. And so it had a base station, which really had all the brains and everything for, and all the telecommunications and everything for Earth. And then it had a rover that was pretty small, probably, you know, a large bread box, I'll call it. And it roved around and took close-up pictures of like this rock and everything, and sent those back for us to look at. So soon after we had that successful landing, they started planning for the next exploration of Mars, which they had planned to launch in 2003. And I'm sure everybody's familiar with the two Mars exploration rovers, Spirit and Opportunity. And those were built as a way to actually explore more of the surface than just a stationary lander, and would give it more roving range than what they had done with Pathfinder, since Pathfinder was kind of limited to stay in a local area of where that base station was. So Spirit and Opportunity were built, they were supposed to last about 90 days. And as you know, they lasted well over 10 years. And they roved and did a lot of exploration of Mars and sent us back lots of imaging. And we learned lots of things about the differences in terrain on Mars and everything. And so after that successful landing and roving, they planned their next mission to Mars, and they wanted to go with something bigger. So Pathfinder was about the size of a large bread box. Spirit and Opportunity were about the size of a golf cart, I would say. So their next endeavor would be to target a launch in 2011, with landing in 2012 with Curiosity. And this rover is fairly large. It's more like a car, compact car. And it successfully landed in 2012 and has been exploring ever since. The difference with this rover is the power. The power for the MER rovers was solar powered, and so they would have difficulty with dust accumulation on the solar panels, of how much power they would get. And so with using RTG, which gives them almost unlimitless power, they're able to rove, of course, much farther with Curiosity. And so Curiosity landed near Mount Sharp, and they've been exploring that region ever since, and have been sending back a lot of good science on that mission. So after Curiosity, the next exploration mission that landed was, that we still have on Mars, is Insight. And so Insight is the project that I'm the project manager on, It landed successfully in 2018 and was launched in May on Cinco de Mayo of 2018, landed, as Heather said, the day after Thanksgiving. It actually landed, so it landed on Cyber Monday, and it gathered so much attention that it actually, the hashtag Mars Landing did better than hashtag Cyber Monday. So it was a very popular thing for people to look at and see that landing. Since then, we've deployed 2 instruments to the surface. There's a seismometer here that's covered by a wind and thermal shield on the left side. And then on the right side, there's an instrument that's called HP3, which is a heat probe. And what that probe is supposed to do is supposed to penetrate using self-tapping mail is what they call it. And it's supposed to penetrate down the surface for 5 meters. We've been having a little bit of difficulty with that and the amount of friction that is in the soil of Mars. And so we've only got it to penetrate down so it's just covered. So we've been continuing to work on that. We do also have instruments that look at the weather. So we have wind instruments, pressure sensors, and magnetometers on board. And we also have imaging cameras. We have a convex camera that takes a picture of kind of this work area in front of the lander. And then we have a camera up here on the arm that can take a picture all around the whole landing area, so we can use that for scientific type imaging. So now, of course, we're all getting set up for Perseverance, so we can take a look back at kind of what we currently have at Mars and what's coming up. So currently, we actually don't have opportunity because unfortunately we lost opportunity on a large global dust storm in 2018, just prior to InSight landing. But we still have a Curiosity rover there. We have several orbiters, starting with the oldest, which is now, I guess, 19 years old, which is Mars Odyssey. Mars Express arrived in 2003, which is an ESA mission, and they give us support in relay. We also get relay support from Mars Odyssey. And then we have Mars Reconnaissance Orbiter, which had arrived in 2005. It returns a large amount of data. We have Maven that arrived in 2013. That is run out of Goddard Space Flight Center. We have MOM, which was a Mars orbiting mission from India that arrived in 2013. The TGO, which is the Trace Gas Orbiter, which is also an ESA mission. It also provides us with relay ability for our landers and rovers. And then, of course, in 2018, I just talked about InSight landed, and in 2020, we have several activities going on in 2020. We have the 2020 rover, which we're going to talk about now. It's also supposed to be a rover, an orbiter from China that's landing. There's the HOPE orbiter that's coming from United Arab Emirates. It's actually supposed to launch the week before Perseverance. And then there is supposed to be an ExoMars rover from ESA landing. For the future, there's a Jackson mission, MMX, that's coming up in 2024. And in 2026, we have a sample return mission that says China on it, this is not my slide, which I believe is wrong. It's we have a mission from JPL. It's called Mars Sample Return that is going to be launching in 2026. And it will be gathering, actually, samples from the 2020 rover. So let's get to the actual main bulk of the talk, which is the 2020 rover, which is Perseverance. So this is an image of it as it would look on Mars. It's very similar to MSL or Curiosity in design. The instrument suite is different, which I'm going to be going over in a few minutes. And it has this much larger arm and instrument capability on the end of the arm. So as kind of a mission overview, they're going to be launching here at the end of the month, as Heather said. And they're launching on an Atlas 541, which just means that it's a 5-meter fairing, 1 centaur second stage. It will go through a 7-month cruise to arrive at Mars, and it'll be arriving February 2021, so you'll want to watch for the EDL coverage on that when we come up to it. It's going to be doing entry, descent, and landing, which is analogous or the same as, very similar to MSL. They have made some changes, which I'm going to be going through in a little bit here. One of the largest changes is they're having to land in a much smaller, what we call landing ellipse, which means what's the target you're trying to get the spacecraft to when you land on the surface. And then they are going to be on the surface for at least a year, Martian year, sorry, 2 Earth years, where they're going to be studying the surface some more. They're actually going to be using ground penetrating radar to look under the surface, and they are going to be caching samples for a later sample return mission. So the mission objectives for 2020 are study geology, to explore ancient environment on Mars, understand processes of formation, everything of the planet, astrobiology, to assess the habitability of ancient environment. So they're looking for evidence of past life, and that's actually where the sampling comes in. They're going to be wanting to take core samples of where they believe there is evidence of possible past life, and then those will be cached and then for later return to Earth. And then they'll also be, there's a couple of experiments there where they are looking at preparing for humans. So they want to measure temperature, humidity, wind, and dust environment on that part of the planet. We do have other temperature and pressure and everything, of course, on InSight. So there's a couple different, I'll call them kind of Mars weather stations that'll give them information to prepare for human exploration. And also they have an experiment on board to take a look at converting the CO2 in the atmosphere of Mars over to simple O2 that can be used for fuel or, human consumption. This is kind of the architecture of the notional sample return mission, which would be launching in 2026. So it'll cruise and land on Mars. This lander here will be more like an InSight-style lander. It'll be propulsively landed. It'll contain a rover on board, and it'll also contain a MAV, which is a Mars Ascent Vehicle. And so the idea is the Fetch rover and or Mars 2020 will bring the samples to the return container. That'll get put into the MAV. The MAV gets erected and then launched. And then that little kind of basketball-sized thing that is carrying all the samples will be captured by a rendezvousing orbiting mission that'll be sent by ESA. And then it'll return back to Earth, and it'll come down in a return capsule to land in the Utah desert. So that's kind of the sample architecture. As far as the rover, if we take a look at the instruments on the rover, there's several. We'll start off with the mass cam. So the mass cam is used, it's a camera system. It's a panoramic and stereoscopic imaging system. It also has the capability to zoom, which we haven't had before. So usually we have to take an image and then we have to drive further up and then take a closer image, or just try to, zoom the image based on the resolution you have on the image you took. This actually has the ability to zoom, which will be helpful. And there's 2 of those. They sit up on the mast here. Then the next instrument is called META, which is the Mars Environmental Dynamics Analyzer. And so that's kind of this weather station where it takes the temperature, wind speed, and direction, pressure, relative humidity. It also measures dust as far as size and shape. And so they'll be using that to see how dust accumulation, in more detail works, because we know that it accumulates on landers we have that have solar panels, or rovers that have solar panels. So when you have human exploration, you'll want to know all this information. The next instrument is MOXIE, and that's a Mars oxygen experiment. That's what is going to be converting the CO2 over to O2. They want to test that out for future human exploration. The next instrument we have is called PIXL, which is the Planetary Instrument for X-ray lithochemistry, and that is an X-ray spectrometer, essentially. It has a high-resolution imager. It actually sits on the end of the arm here, and so they're able to put that up against where they want to drill and look for this ancient evidence of life. So they use that as part of the suite for doing that. The next instrument is RIMFAX, which is a radar imager for Mars subsurface experiment. And that's a ground-penetrating radar that will provide centimeter scale resolution of the geologic subsurface. And so they'll use that to take a look at under the surface of Mars using a radar, which will give them some idea of what is below them. And I believe that is also on the mast, sorry. And next we have is Sherlock. So Sherlock kind of works in conjunction with PIXL, and it's scanning habitability environments with Raman and Lumen Science for organics and chemicals. I can never do that. So it's a spectrometer that will provide an even finer scale imaging and uses ultraviolet laser to determine meteorology. And so it's used in conjunction with PIXL. It actually sits down here on the arm and gives them a closer look that also helps them decide what samples they want to take. As we keep moving forward, we get to SuperCam, which is a instrument that provides imaging and chemical composition analysis and meteorology. And the instrument will be able to detect the presence of organic compounds and rocks and regolith from a distance. And it's also a significant contribution from the from the French space agency CNES. And so they provided that instrument. I also neglected to say back on Meta that the wind sensors on Meta were provided by the Spanish space agency. And so we have international collaboration. We also have an antenna on RIMFAX that was made in Switzerland, I believe. So those are kind of the suite of instruments. The electronics are mostly in the main part of the body of the rover, and then the actual sensors are usually on the outside, either on the mast or up on the arm, to take a look at the environment and the surface of Mars. So this is a little more information kind of on them, which I kind of already covered. So MASCAM, RIMFAX, and all the instruments I went through, these are kind of examples of what they return as far as information. The ones most people are interested in, I think, are PIXL and Sherlock, which take a look at the chemical and mineral mapping, and so they help select the sites we want to do the actual sampling and borehole science that we'll be doing. So as far as the sampling and caching subsystem, so there is what's called a bit carousel, which carries all the individual bits. And there's approximately 42 sample tubes on board the rover. And so what they do is they find a location they're interested in to take a sample so that it can be studied later. and they use the robotic arm to get a bit out of the bit carousel, and they go ahead and they bore where they are interested in the sample, and then that sample and bit is put into a sample tube, and then that sample tube is sealed and then ready for caching. So if I move down to the next one, this is a little bit of information on the coring and samples and witness. So there's a coring bit here, and that gets hermetically sealed in this sample tube, which this is kind of a cutaway view of that. Sample tubes look like this, so they're little, they're little tubes, and those tubes will hold the sample. They'll be sealed in there, and then they are deposited onto the surface in what we call caches. And so they'll deposit a group of them from a location kind of together once they've done several sample tubes. And that, I'll call it a pile or a cache of tubes, is then returned back to the Mars sample return mission years later by either Perseverance or by the Fetch Rover on the sample return mission. So let's talk a little bit about landing site. So the landing site they've selected for Mars 2020 is Jezero Crater, which you can see. You can't really see here because this is far away. This is Columbia Hills, which you're familiar with from the MER rovers. And if we zoom in on that segment, this is Jezero Crater right here, and it lies right next to this plain, Planitia. And if you kind of look very close at it, it looks like this is an impact crater that's in the middle of what looks like a delta, right? It's like this is water. It rolled down here into a delta. And so, so they're interested in looking at this area and sampling from this area. But if you kind of look around, there's a lot of features and everything here. So landing there is going to be a challenge. So I'm going to talk a little bit about the landing. And that is, the landing system is very similar to Curiosity. It's using this, what we call the sky crane, which is the part up here. And it gets lowered down on tethers as the last part of the landing as it's being propulsively brought down near the surface, and then it cuts the bridles off and leaves the rover. So that landing system that we used for Curiosity, we're using that same type of landing system. Although we've added some additional landing capabilities that'll give us some more information, especially for or also related to human spaceflight, because it'll give an idea of what entry, descent, landing really is. It'll measure some of the things more closely. So as far as landing, to give a comparison, Mars Pathfinder, they had a landing ellipse that was 200 kilometers by 70 kilometers, which is fairly large. Phoenix and my mission Insight, we had a ellipse that was about 130 kilometers by 27 kilometers. MSL, when they landed, their landing ellipse was 25 kilometers by 20 kilometers. And Mars 2020, they need to land in an area that's about 7.7 kilometers by 6.6 kilometers, so much smaller. There's also going to be a similar type landing ellipse for Mars sample return because they have to get actually very close to where Perseverance is going to land so that they can collect these cached samples. So they'll have possibly even tighter landing ellipse than 7.7 by 6.6. So in order to try to get that down accurately, they're going to be using terrain relative navigation, which is new. And so they're going to be looking at after they drop the heat shield off of the aeroshell, then it allows them to then take images of the surface and then compare those to orbital maps of features on the surface, and then allows them to use the thrusters on board to move the vehicle over before separating from the parachute so that they get a more accurate landing for where they want. That's how they're able to get the constraint down and the landing ellipse so small. So the other thing we've added on here are several heating sensors and pressure sensors to take a look at what the airshell, more closely what the airshell goes through during entry, descent, and landing, which will be useful for future missions in human spaceflight. So they've added a suite of these instrumentation on there for entry, descent, landing. We've also added some additional cameras for EDL. So if you've ever looked at the, and this is an image from the camera looking down from MSL, when the heat shield was dropped off, you can see it dropping down to the surface of Mars. We only had this downward looking camera during landing for MSL last time. What they've added is they've added these series of cameras so they can actually look up when they're in supersonic flight and see the deployment of the parachute and see how that all works in detail on Mars. They also have a downward look at the rover as it's being lowered down on the sky crane. And then they'll also have an upward look from the rover looking at the sky crane as it gets dropped off and the tethers are cut and it flies away. So they'll get a better understanding of how all those components are working. So those are all new EDL cameras. So post-landing, they'll play all that data back, and I'm sure that's going to be very exciting to combine all those images so that we can see how things exactly work during EDL. So the next thing I have is not a slide, it's actually a video, and I'm going to play it. It's only about a minute, and this is kind of my last slide. On board Perseverance, we're very excited to have Ingenuity, which is a Mars helicopter. It's going to be the first time that's ever been done where we've flown another vehicle on a planet to take a look around. And so it's actually mounted to the belly of the rover, and it gets dropped out off underneath the rover, and then the rover drives away, and then it is able to go ahead and fly and then explore and sends its imaging back using the rover as the base station. So I'll play this. I don't know how well it'll play, but we'll see how well it plays. So it was about a 1-minute video. As it says there, it's a technology demonstration. I didn't do the sound on this because I don't think it'll come through. So you see how it's dropped out of the belly and it's left on the surface. And then it's controlled from commanding through the rover to it as a relay to the helicopter, and then it'll execute its commands to go ahead and fly. And it'll do the flight pattern that's been given to it in the commanding, and it'll do any imaging that it needs to do that was commanded for it. So it'll fly around and it'll show, I believe, that there's a camera on the bottom, so it takes images below it, so you can see kind of the surrounding area from a different vantage point. And then it flies back to a particular landing spot. And then once it lands, it actually then sets up and transmits all its data back to the rover so that it can be then relayed back to Earth. So that's kind of Mars 2020 in a nutshell. And I think we're ready for questions. I think I will take the presentation down, I'm assuming. Is that what you want to do, Heather?
You can use it as a visual if you want, unless you turn on your camera as people are asking questions if you wanted to say hello or not. It's up to you. Okay. I just wanted to ask one quick question to you, since we're talking to the DSN folks, the Deep Space Network, as well as Barstow Community College. So I wanted to hear from you the contributions that the Deep Space Network contributes to, these huge, not only these huge launch and landing events, but throughout spacecraft communications, the life cycle of the mission.
Okay. I could do that. Actually, you know, being at JPL for so long, I've held many different positions. And the position I held just before I was the flight system manager on Insight was I was what was called the commitments manager for the Deep Space Network for about 3 years. And that meant that we set up all these interfaces and negotiated use of the DSN for different missions, whether they're JPL missions or Goddard missions or scientific use of the DSN just as a radar. But we also do, of course, foreign collaboration. That's what we did with India for MOM, and we're doing with the United Arab Emirates for HOPE. And we'll be doing that, I'm sure, a lot in the future for also human spaceflight. So the DSN is an extremely valuable part of this whole equation. In order to get this data back, and in order to have a mission so you can see all these beautiful pictures or analyze all this beautiful science, you have to have a way of communicating with it, and the DSN does an extremely fantastic job at doing that, and it's a very unique asset in the United States, and we have partnerships around the world where we partner, of course, with Madrid. In Madrid, Spain, we have a DSN station there, and in Canberra, Australia, and all of those are used in order to cover all of these deep space missions and even moon missions, and even in some cases Earth orbiting missions. And it's not only used for just communication, it's also used for doing things like near-Earth observations using the radar at Goldstone and many other things. So it's an invaluable part of the NASA family and gives a large contribution in supporting the missions and just to NASA itself in science.
Excellent, thank you. Just one other thing I was thinking about while you were talking about the entry, descent, and landing that people might not be aware of. There's a lag time in communicating with the spacecraft, so we don't know until several minutes later, right, whether it landed successfully or not. And that means that that whole system that you saw in place, you know, the parachute, all these thousands of steps that have to happen perfectly are all automated. So when that, you know, shell pops off and it's looking for where it should land, all automated. It's not real time, like controlling it from Earth. So that's why it's such a nail biter, right?
Right, exactly. I remember there's a video you can see that has Adam Stelzner, and when they did the Curiosity landing, that explains that. They also did one for Insight that was done by Rob Manning, and those are very good explanations of EDL. And you're absolutely correct. The what we call the one-way light time, which means once you send a signal from Mars, it's traveling at the speed of light to reach Earth. But even though it's traveling at the speed of light, which is extremely fast, it still takes it at a minimum 7 minutes to reach the Earth. Sometimes longer, depending on where you are in the orbit period. And that whole sequence ends up happening in 6 or 7 minutes, which means from the time it starts its entry, descent, landing at the top of the atmosphere till it's actually safe on the ground, gets all completed automatically in an autonomous way, unaided, and you don't see the result of that until after it's completed its landing. So that's a very good point. People, yeah, when you deal with deep space, there's a lot of lag time. So, for example, even when we talk to Voyagers, which the DSN still does, even though it's outside our solar system, it takes them, you know, I think the one-way light time last time I knew was like 13 hours. It's probably longer than that now. So if you want to send a command to Voyager, you have to send a command now, and it doesn't reach it till, you know, tens of hours later. And then when it responds, it sends back a signal, which takes tens of hours to get back. So you don't see it till at least the next day that command successfully got to the spacecraft. So working in deep space and telecommunications, there's there is a lot of lag, which is sometimes hard for people to understand. It's not like controlling a remote control car or something.
Right, and I see there are a lot of questions in the chat box, so I'll turn it over to Leslie to start with a couple of those, if you don't mind, Leslie.
Hi, thank you. Thank you, Heather. Thank you, Chuck, so much. Our first question is from Vanessa, and she asked, what resolution do the cameras on the Rovers have?
Oh, that's a good question. And unfortunately, I don't have that off the top of my head. I can see if I can find it. But yeah, I don't have a good answer for you. I mean, the resolution is such that it's well, you've seen the images from Curiosity, and so they will have hazard cameras like that, and it will take pictures like that. But the actual mass cam and all that, they have much higher resolution. So let me see if it tells me in the mass cam instrument information I have. It says image resolution. So it's able to resolve between 150 microns per pixel, or 0.15 millimeters, or 0.0059 of an inch, to 7.4 millimeters, or 1/3 of an inch, depending on what the distance is. So that's for the mass cam. For the other cameras, let's see. I don't know if it'll have it in here, but that gives you an idea. At least mass cam is extremely high resolution. So it does not say on these other ones how much it is. I would have to get back to them with that answer, but it'll at least give you an idea on mass cam what the resolution is.
Chuck, and I was able to find, they actually have a really great website for Mars 2020, and the Rover cameras are listed there, and it has those resolutions. So I posted that link in the chat for Vanessa.
Thank you.
Thanks. So two questions that kind of go together. Let's see, talk about the launching date, right? And the reason behind why we are launching at this time, and then the landing site and how the team picked the Jezero crater as the landing site. Can you touch on those?
Yeah, so when we launched to Mars, we were in what they call opposition every 2 years. So what you want to be is in the position where the Earth and Mars orbit periods are such that you have the shortest cruise time. And so the cruise time, when you launch at those particular windows, are around 6 or 7 months worth of cruise time, depending on when exactly you launch, and it varies a little bit every 2 years. But so we set up to launch every 2 years. It rotates slightly because, of course, the orbit period of Mars is, I think, 686 days, and the orbit period for Earth is 365 days. So you're trying to get it lined up so that when what you got to remember is when you launch, you want to be in a position so that when you arrive, you're going to arrive 6 months later. So your distance from Mars varies. So the distance, might be, I think it's something like 160 million miles or something on Mars, but the actual distance the spacecraft travels is around 350 million miles or something like that, and in order to reach Mars. So it travels actually much further, but it's actually the shortest distance you can go between the two. So they picked the launch date based on that. So that's why if you don't make the launch date, so for example, if we go outside the launch window for Perseverance, you can have to delay up to 2 years. That happened on InSight, where we didn't have an instrument ready. We were at the launch pad. The instrument was not ready to be integrated, and so we were going to miss the launch window, so we had to delay 2 years on InSight and launch in 18 instead of in 16. So those periods are very important, and they're all based on what we call orbital mechanics, which is where are the planets with respect to each other at launch and when they arrive. As far as the selection of Jezero Crater, I don't have very much detail on this, except for to say, I know they were looking for an area where they felt that there would be ancient life possible to be able to see that. They were selecting from 3 sites. Jezero Crater was one, the Columbia Hills was another, and I forget what the third one was. But they looked at those 3 sites, and they tried to select the one that they thought would give the most and best, richest samples on having success of looking for, when it's returned to Earth, that there would be ancient life that they could identify. So that's how they selected the site.
Wonderful, thank you. The next question is from Jason, and he asks, is there a course of action if the parachute on board fails to deploy? Is there a reserve parachute?
Unfortunately, there is not. So all of these systems are tested extensively to make sure that there is no kind of glitch on them. So they test for example, like you're asking about the parachute. So they test that supersonic parachute in a variety of different ways, including things like, that's important to us, which is kind of less important if you're like a skydiver or something, is something called bag strip. So it's, how does the parachute actually leave the bag when it's deployed out? And that always has to be a known thing and very smooth, you know, whereas when you pack a chute, you know, for skydiving or something, things can go wrong with that, and they, you know, that's why you have a reserve chute. On the Rover, they have a particular procedure that they pack it exactly the same way every time, and they make sure that it deploys out and the bag strip is good on it every time. So I'd say how they mitigate it is not with a reserve chute, but they mitigate it by extensive testing of how the parachute deploys. And that's true of the other parts of the landing system, by the way. They test those extensively to make sure that all of those work correctly. And there are some parts of the landing system, if something is having a problem, it can bypass. But there are a couple points that if you don't have it, it can be an issue. And that's also why it's very hard to land on Mars. That's why you have things like what unfortunately happened to the Schiaparelli lander, where it doesn't actually land, is because it's a very complicated thing with thousands of steps. And if something goes wrong, it is very possible for you to get an unsuccessful landing. So that's why it's important that you, you know, test it and then test it again some more. So that's what they do in order to ensure successful landing.
Wonderful, thank you. The next question is from David, and he asks what the differences are in the core drill device compared to the one that is on Insight.
Oh, well, the drill on Insight is not really a drill. The drill on Perseverance is one like a classical, you know, drill that you have to drill through wood or something. It spins and it bores through, and then it has, you know, a hollow center, and then it pull, you know, that sample is able to be kind of broken off and then pulled in and put into the tube. The quote drill on Insight is really more like a jackhammer. So it has a motor inside of it that it spins around and then drops off an edge, and it puts, you know, a lot of force downward, and then the recoil is absorbed by what we call the mole, and then it just keeps doing that. So it does something called hammering. So it's more analogous to a jackhammer as the drill instead of an actual drill.
Excellent, thank you. And the next question is, how does JPL go about interacting and receiving help from other nations, like how Switzerland donated a part to the rover?
So what they do is, at the very beginning of the mission, when we're first planning the mission, we're in a very early phase where we start looking at what's the concept of how we're going to do the mission, what does it require, you know, how do we land, what instruments do we need, and everything else. And then what they do is they decide on what parts that they may want to not build, what we call in-house or at JPL, and what parts we do. And so the ones that are not, or instruments that they're not, they put what's called a call out for those instruments to the scientific community. And of course, that scientific community is large, and it includes all of our foreign partners like CNES and the DLR in Germany, or ESA, or any of those. And so then these people will look at, okay, they need to have an instrument that does X, Y, Z. And so we think we can build an instrument that does X, Y, Z. And so that what they do is they propose back to the project that they could do this instrument and how that instrument would work. So that's how they kind of collaborate, and then those are negotiated, and they're usually negotiated. There's not an exchange of funding. There's usually an exchange of scientific data or something. So they say, I'm going to provide instrument XYZ to you, and I want you to return not only the scientific data of that, but some other scientific data from instrument ABC to me. So there's usually an agreement made of exchanging information and stuff in order to provide those instruments. So that's how that works.
Excellent. We love our international partners. The next question, is are there plans to explore the north or south pole of Mars, since it seems like they would have different weather conditions compared to the rest of the planet?
Well, there was a mission called Phoenix that was sent that looked a lot like InSight. Trying to remember, I believe its landing was, I want to say 2016. I have to look it up. But it landed closer to, I believe it was the North Pole, and they actually used a scoop, and they took samples and put it into kind of like a spectrometer or a way to analyze the content of the sample. And they also dug down, and they were able to find ice under the surface. They could actually see it when they initially landed, because the thrusters actually kind of dig out the surface of the planet slightly when you land by, a few centimeters or so. So what they found was there was ice just, a few centimeters under the dusty surface. So there has been some amount of study of that by Phoenix, but I'm sure there will be more. That's kind of more of a scientific question. I'm more of an engineer, so it's dependent on what they have in what we call the decadal survey. So they look 10 years ahead, a decade ahead, and they look at what do we want to study on Mars, or what do we want to study as far as astrophysics or something else, and they make a priority as to what they're going to study. And whether the poles are in there or not, I'm not sure, but there has been at least one mission that kind of met the spirit of that, I would say.
Okay, thank you. Several of the questions have to do with potential damage to the rover and what would be done, say, if like a camera broke, or about the weather on Mars potentially damaging the rover.
Okay. Well, I kind of doubt that the weather on Mars would damage the rover, especially this one, because it doesn't have solar panels. So it's not like you see on the Martian, where it's a big dust storm and people are going to go flying around. They do have dust storms, but they're different than what was depicted there. But it can get damages in other ways. Let's say we accidentally run onto something, or I don't know, right? Or sometimes we just have an issue where, even though we've tested the heck out of something, something will fail. So a lot of times the way we get around that is that's why we have like two cameras on the mast, or we'll have backup sets of electronics. So there'll be a primary, what we call a primary side, and a secondary or backup side. And so we have redundant equipment or redundant electronics a lot of times to cover that. Some instruments don't, but a lot of instruments do. There's usually some way to try to recover. So for example, for my mission, the mole trying to penetrate the surface of Mars, was having a problem doing that. So we actually did something that we thought we would never do, is we used the robotic arm to remove the support structure from the mole and then we use the arm to interact directly with the mole in order to get it to penetrate down deeper than it had. So that's kind of an example of, you know, if you're really thinking about things hard and you think outside the box, you can think of some way to usually help with those situations. But the short answer is usually backup electronics or redundant cameras are usually used.
Okay, thank you. And Winnie and Kaylee have very similar questions about what happens to the rovers when they are out of commission. Will we ever retrieve them? And what kind of new advances does this current rover have from the discoveries of the old rovers?
Okay, so as far as retrieving the rovers, I would say there's no immediate plans for anything like that. Just like we left the surveyors and on the surface of the moon, and we left the landing modules from the Apollo era on the moon, there's no current plans to collect that. I mean, I imagine hundreds of years in the future, somebody may want to do that. But currently we leave those where they are, and there's no plan to collect them. Although in some ways I've always felt that probably is interesting to take a look at them some amount of time afterwards, but currently there's no plan to do that. And the other part of the question was, I'm sorry, I forgot the other part.
It was what's the new technology or the new discovery?
Oh, yes.
Yeah.
Yeah, so the new technology, a lot of these instruments are new technology for the rover that are beyond what was on Curiosity or the MER rovers. And they're really geared specifically to take those samples, analyze the surface of Mars more closely than we have in the past. So the cameras are have higher resolution. The instruments have more information that they're gathering as far as being able to tell what the chemical makeup is. And then we have, of course, this caching system so that we can actually store the samples. And so I think it's hard to kind of quantify without having kind of you'd have to have like the scientists for each of the instruments probably explain that better, but they are more advanced. There's more instrumentation on this than have been on previous rovers, and of course this caching system, which will allow us, when we bring the samples back, to actually study them in extreme detail, because of course they'll be here where people can actually interact with them directly.
Thank you, Chuck. It is 11 o'clock now. Do you have time for one more question before we do closing remarks?
I sure do.
Thank you. So the last question from Jason is, how has SpaceX, or what has SpaceX contributed to the advancements of space travel, specifically to Mars?
Well, I guess SpaceX is of course, a company that's been in human space flight more. They've also been launching unmanned, a lot of communication satellites and stuff. I think in a short amount of time, they've made great progress as far as, I'll say, catching up or maybe even surpassing the United Launch Alliance suite of launch vehicles. And so I think they're going to play a large role in the future as far as looking at the architecture of getting humans to the moon and beyond. They have these heavy launch vehicles that have the ability to get a capsule size that they're using for Dragon to Mars and possibly land it. To possibly land it for human exploration. So I think that they're poised in a good position to be a large contributor to future unmanned and manned missions with NASA and other space agencies around the world.
All right. Well, this is Heather Doyle again from JPL. I just wanted to say thank you, Chuck, for taking your time to give this presentation. I know everybody who works on Mars is extremely busy right now. That it's an all-hands-on-deck scenario, and you, of course, have insights that you're watching over. So I really appreciate you taking the time to talk with us. And I did want to mention a few campaigns that the public can be involved with. I just put them in the chat box. We did, for the launch coming up, create some cool Instagram filters. There's 3 different filters so that you can use, and I have the link there where you can find them. You may have participated in the Send Your Name to Mars campaign with this rover. There are almost 11 million names on a chip going up with this rover. So if you want to go back to that website, which I've put the link in the chat box, you can get a stamp on your boarding pass, because if you remember when you sent your Mars, when you sent your name to Mars, they gave you a boarding pass, and now you can have that now boarding stamp put on your boarding pass and print it out again if you want. And for those who missed sending their name to Mars, you can actually already start putting your name in for the 2026 launch for that follow-up mission that he described as far as the sample return goes. And then finally, we have a fun campaign where you can submit a video where you're doing a countdown, similar to what they do, at a launch where they're, saying 3, 2, 1, lift off. You can record your video. There's a link there on how to participate. So those are some ways that you can get involved, and just don't forget to keep an eye on when that launch is going to happen. Right now it's July 30th, but it does move. But the landing will be February 18th. That doesn't change. So keep an eye out for both of those things. I don't know if Dr. Bragg or Anthony has anything else to say before we go.
Heather, Mr. Scott, thank you so much. You can see from the thoughtfulness of the questions, just great engagement. People are so appreciative of a wonderful presentation, lots of interest. Thank you so much.
Yes, thank you. I'd like to echo that sentiment also to Heather and Leslie for bringing this opportunity to the Barstow Community College and our region. And Charles, thank you so much for sharing your infinite wisdom. And we're looking forward to many more of these types of lectures for our community.
Thank you for having me. I appreciate it.
All right. Well, stay safe, everybody, and we'll see you next time.
See you next time. Bye-bye.
Bye.